G'day everyone. I hope you survived that assignment okay. Welcome to our last lecture of new content. End of week 11, you're just about done with this class. And I believe I've got Zoom going, and at this point it looks like it's holding up nicely, so hopefully you'll get no buffering on the stream, and we've got a Zoom running as well. So if you have a question on Zoom, you should be able to just shout out and ask me the question out loud now, unlike in previous weeks. Sorry it's taken so long to get this working. I had a whole bunch of technical issues that stood in the way of that, but it's working now. And it should actually be quite, if it works well for this lecture, it'll be great for the revision lecture, which is on Monday. All right, with that, let's get on with the content of the lecture. Here we go. All right, presentations for next week. That's the most important part. Your labs are on next week, and during your labs you'll be doing presentations. And your presentations are done via video and then Q&A. If anyone has any questions about how to do that, please say so. And but it should be clear enough. Great. Okay. Now assignment 2, that's done now. The deadline's gone. And someone asked before about whether you can share your assignment with others. And the answer is just wait till 5 o'clock today in case there's something comes up, just to allow a little bit of grace in case something strange happens. But basically, yeah, you can share your assignment from 5 o'clock onwards today. You can discuss how you solve the problem with anyone else. There's no problem with that at all because the deadline's passed. On Monday, we've got a 2-hour revision lecture, and the way I'm going to do that is, first of all, I'm going to focus primarily on the on the sample exam, which I posted on the course website, and on it's on GitLab, and I mentioned it in Piazza as well. So I'm going to focus on that first, and I'll work through that. What I would like you to do is I'll post probably. On the weekend, I'll post a thing for the coming week, and in that I'll invite you to write comments in Piazza below my post saying what things you'd like me to discuss in the revision lecture. So if you think things you'd like me to discuss, please let me know. The more precise your question is, or more precise your request is, obviously the more able I'll be able to give you a good coverage of that question. So that broadly I can talk about mechanics of the exam. Obviously that's not very interesting, but it's pretty important. I can talk about very specific things in the course content, but one of the obvious things is in the sample exam there are lots of questions there. I'm not going to go through all of those, but if there are ones you particularly want me to go through, just let me know, and I can try and go through those during the lecture like I did for the mid-semester exam some weeks ago. All right, with that, I think we're ready to move on, unless someone's got a question. Again, now that you're on Zoom, for those of you who are on Zoom, you can just ask your question out loud. I won't be watching the chat on Zoom. If you're on Zoom, please don't put stuff in the chat there, because I won't be able to watch that as well as Teams. So if you're on Zoom, the way to ask a question is either to type into Teams or to ask out loud. All right. We did C5 on Monday. But I was frustrated to see that my graph for the binary search tree didn't do what I expected. And I thought about it for a bit, and I realized right after the lecture what was going on. Did anyone else work out what the problem was? What I expected to have, and some of you correctly suggested in the lecture, that if we had a dictionary which was sorted, and we put it into the binary search tree, then actually the behavior of the binary search tree would be like a linked list, right? That's what people said in class, and I agreed with you all. That's absolutely right. However, it didn't behave that way, and I couldn't work out why. I was a little bit stumped in the lecture, and right after the lecture, I went and looked at it, and it suddenly dawned on me that there's a very clear reason why that wouldn't work, and that is our binary search tree, the way it sorts elements in the tree. If you go and look at the code, let's have a quick look at the code to make this really clear. Let's have a look here. Maybe someone here. What was it? A set, wasn't it? BST set. There it is. Here, let's see how it. Okay, there's an example of how our binary search tree finds stuff in the tree, right? And here's another one for adding, right up here. Can you see that? Can anyone see why the dictionary, which has got all the words in alphabetical order, did not go into a linked list? It didn't behave like a linked list in the lecture last week, in Monday's lecture. Can anyone see the answer? I can see the answer staring us in the face right here. The answer is that we didn't. This does not sort the elements of the tree alphabetically. It sorts them according to the hash code. And the hash code doesn't necessarily have anything to do with the letters of the alphabet. Okay, so our dictionary, although in lexicographical order, although the dictionary is in lexicographical order, it will the hash codes could be in arbitrary order. The hash code for AAA or aardvark could be higher or lower than the hash code for zoo, right? There's no particular relationship between them. They're quite unrelated ideas. So someone's asking on the chat about what's in the exam. Basically, everything's in the exam. There won't be coding questions on JavaFX, but there could be a multiple choice question on JavaFX like there was last semester. If you look in the sample exam, you'll see there's a fairly straightforward multiple choice question on there. Well, when I say straightforward, I mean it was a well-contained question. It was a multiple choice one, and the substantive question that was asked in the mid-semester in the sample exam was not really so much about JavaFX, but about event handling, which is a more core concept. Okay. Is exam open book? Please take a look at the web page. The course web page explains all this stuff, but you guys are asking questions that are really well explained. Here, look here. We go to assessments. We go to final exam, and here it tells you about it here. Okay, and there's a sample exam. Is it open book? It tells you here it's not open book. I mean, it's open book in that you can use any of the materials from the course and you can look stuff up. You can even look stuff up online, but you can't communicate with anyone else, okay? Anyway, please read the course website. It does explain a lot of this stuff. Let's not discuss the exam much further here unless you've got an urgent question. That's the subject of Monday's lecture, right? Monday's exam revision. And let's get back to what I was trying to talk about, which is this. And I was trying to explain why the computational complexity was not what we expected. I hope people can understand that. Does anyone have any questions about the computational complexity question? We were expecting when we added the dictionary to the binary search tree that it would degrade into a single linked list because the dictionary was in alphabetical order. However, as you can see from this, our binary search tree actually used the hash code of the words, not the alphabetical ordering of the words. Therefore, it wouldn't have done that, which explains why we saw what we saw in that lecture. All right, any other questions on this? Nope. All right, that was all I wanted to do on the computational complexity. So now moving on to the substantive content of today's lecture, we're now going to talk about concurrency. And I want to start off by asking you all to think about the English word concurrency and to think about what you know about concurrency or how you might explain concurrency. Can anyone try and give an English definition to the word? When I say English, I mean non-technical definition of concurrency in real life. Anyone want to offer a suggestion either on Zoom or on the chat? What does concurrency mean in English? Doing many things at once. That's not bad. Ben Alexander says doing two similar things at once, doing multiple things at the same time. Okay, these are all great answers. Okay, we're going to get more technical and more particular, but multiple things happening at once is the general idea, and multiple things happening at the same time. That's the general idea. Okay. Now we also have another English word that has a more particular meaning in computer science, and that is parallelism. Does anyone have a sense of what parallelism means in the sort of more loose, general, non-technical sense? Anyone want to try for that, either out loud on Zoom or in the chat? I haven't heard anyone say anything on Zoom. I trust that my speaker is working. Someone says something about not interfering with each other. Things happening side by side. Anyone else? Okay. Well, I'm going to walk you through some examples. You know, I love analogies, so I'm going to walk through some concrete, real-world analogies, which I hope might help you get a really good grasp on this. Because actually, a lot of the concepts we're going to discuss right now are ones that that you actually have a fairly good intuition for in real life, if you think about it the right way. And I'm going to try and channel your thinking. Okay, first of all, I want you all to imagine a huge grocery store, like the biggest grocery store that you've been to, the biggest regular sort of grocery store, like a giant Coles or something like that, or Woolworths. Okay, a big one, right? And I want you to think about all of the workers in the store. who they are and what they're doing at any moment in time. If you walk into that store right now, what are people doing inside of that store? What are the activities? Think about the workers there inside that store, okay? Now, hold that thought. Now what I want you to do is to think about, if you've ever been to a 7-Eleven late at night, like at 2 o'clock in the morning, there's often just one person there, right? Just a really small store. And I want you to think about what goes on in something like a 7-Eleven. The point is, the idea of the 7-Eleven is just that there's a single worker, okay? Think about the task that single worker has to do in the 7-Eleven, right? I want you to think about what the person in the 7-Eleven is doing. They're doing stuff like they're ringing up sales on the checkout. They're taking people's money, right? That's one thing they're doing. They're possibly fixing the coffee maker up. Maybe the coffee is making coffee and it runs out and they need to top that up. Maybe someone spills something on the floor. They've got to mop that up. Maybe they've got to put stuff on the shelf. Maybe they ran out of something and they have to go get stuff from the store and put it on the shelf. Okay? There's a multitude of different tasks that a person inside of a 7-Eleven is doing. But there's just one person and they're doing all those tasks. And at any moment in time, that one employee can only be doing one of these tasks. Well, basically. Okay? That's the key idea of the 7-Eleven. I just want to get that idea of the one person working there. I mean, of course, we talk about multitasking in informal English, but in practice in the store, really, that person can just be doing one job at a time. If they're mopping the floor and you come in and you want to buy something, they need to stop mopping the floor, go to the checkout, and then they can do your sale. Okay? Conversely, if they're out of milk, they're going to have to stop doing sales, stop mopping the floor, go get them extra milk, put it in the fridge, then go back and do whatever they're doing before. One person. Okay? Now, let's go back to the big grocery store and think about what's going on there. Okay? And I want to suggest to you that concurrency in the computer science sense is when two or more things are happening at the same time. Two or more workers are working at the same time. Now, in the 7-Eleven example, there's only one worker, so there's no concurrency in that contrived example. Okay? But in the grocery store, there's going to be concurrency, right? The big grocery store, the big Coles, it's got, say, 20 people on the floor at once, right? Or 15 employees on the floor at once, right? And the other thing I want to suggest to you is the idea of parallelism. That the way we want to think about parallelism is a single job being done by multiple agents at once, multiple workers at once doing a single job. So they're making one job go faster by having a lot of people do it at once. Can anyone think about the grocery store, about examples of concurrency and example of parallelism? Can anyone think of examples of concurrency or parallelism there? Nope, everyone's gone quiet. I know you're all really pretty tired from the assignment deadline. No examples of parallelism or concurrency in the large Coles. Really? Stocking shelves. Okay, so stocking shelves. Okay, Ben says stocking shelves. Is that parallelism or concurrency or both? Stocking shelves is a great example, but I want you to try and be specific. Is stocking shelves parallelism, concurrency, or both? Serving people, parallelism. Okay, the checkouts are happening in parallel. Imagine there's no automatic checkouts. It's just a whole lot of checkouts in a row, like say at Aldi, I guess, right? A whole lot of checkouts. That would be parallelism. All of the people who are on the checkouts, say you got in a giant Coles, you got 10 checkouts, okay? 10 checkouts and there's 10 staff there. Those 10 people are trying to serve as many customers at once. You could just have one person serving all those customers, but if you have 10 people, in theory, you're going to go about 10 times faster in that parallelism, okay? 10 times faster in the parallelism if you've got 10 people serving all of the customers. And they're all doing the same task, serve the customers, do the checkouts, right? So that's what we call parallelism. That's an example of parallelism. Now, if we go to the example of stacking the shelves can also be parallelism, because you could have, if you go in there late at night, you might see 2 or 3 or 4 people stocking the shelves, right? So that would be parallelism. But it's also happening concurrently with other tasks. Someone's mopping the floor. Likewise, the checkouts is also happening concurrently with the person mopping the floor, or the person doing security, or the person answering questions at the desk, or the person who's operating the deli. So all these people have different roles, and many of them operating concurrently with each other. Some of them are also doing stuff in parallel, like the 4 people who are stocking the shelves, or the 10 people who are doing the checkouts. They're operating in parallel, So that group of 10 is parallel doing the checkouts in parallel, and that group of 4 is doing the shelf stocking in parallel. But they're all operating concurrently. Okay, so they're all operating concurrently. Now what I want you to do is think about if you go to one of those stores, you can buy stuff like olives. You can buy it already in a jar, but you can also go to a deli and buy those things, or some cheeses and stuff, or some sliced meat. You can buy them at the deli. Okay. Now the thing that's interesting there is a lot of customers might want to go to the deli at once. Now if you had one server, one worker, and a lot of customers, then it's pretty simple, right? You just make a line for all the customers so that they all get treated fairly, right? So all the customers line up for the deli, and then the one person who's behind the deli serves one customer, and then when they're done serving that customer, they get the next customer, and they serve them. But if you've got 2 workers, or say 4 workers behind the deli, how do you make sure things are fair? Okay? Because it's a little bit hard to do that well. Well, there's a very simple mechanism, and actually, we actually use that one in computer science. We call it a deli counter. And that's exactly the way it works in a real store. If you've been to a real store, you'll find that often what happens is you pull a little bit of paper out, or you press a button, and it gives you a number, and then your number comes up, right, when it's your turn. Okay, so then you can stand back and just wait until it's your turn, and then when your turn is up, you get served. Okay, and that allows for or some number, more than one server, to serve lots of customers all at the same time in a fair way. And all that needs to happen is the customers take their ticket when they arrive, and then they'll get served in that order. Okay, independent of which person ends up serving them. Okay, does everyone familiar with those ideas? Hopefully what you've got there is a fairly clear picture of concurrency and parallelism through the lens of a grocery store. Okay, and hopefully it's really obvious to you how you can make more customers be served more quickly by having more checkouts running at once. And you can stock the shelves more quickly if you've got more people stocking the shelves. Okay? But there are limits. Now I want you to go now, switch lenses. Let's go to a restaurant now, and let's go to the kitchen, a big restaurant kitchen. Okay? And you've got a whole bunch of tasks that need to be done there. And you've got maybe one head chef and a whole bunch of other people working for that chef, a whole bunch of cooks, chefs working for that chef, and they've got a lot of jobs to do. All right, and one of the jobs among many is salting the soup. Someone's making soup, and you've got to put salt in the soup. Okay, more salt needs to go into the soup, and it's critical that it happens. You don't do that twice, right? You don't want to have accidentally put in twice as much salt, right? So it's a big pot, and you put in a large amount of salt in this huge pot, but you don't want to accidentally put twice that amount in. You don't want 2 people to put the salt in, right? That would be a disaster. It would spoil the soup. Okay, the soup's dead, right? You have to throw it out and start all over again. That would be really, really bad. Okay, so how can we avoid this, right? There are many ways you can avoid this, but imagine that you had diffuse responsibility. So there are multiple cooks, and it's not the case that just one of them does the salting. It could be any one of them who does it. Okay, so and it could be that what you did is you had a little piece of paper that says whether or not you salted the soup. So you go and check that piece of paper to say you're salting it, and then you go and salt it. But what happens if you just go in to check it, and then you get interrupted and you forget, and then the soup won't get salted, right? On the other hand, if you salted the soup and then went to check, but just before you went to go and do the check mark, someone interrupted you, and while you had your back turned, someone else came and said, oh, someone hasn't salted the soup. And then they go and add it and do the check mark. And then suddenly the soup's been salted twice. Okay, how do you solve that problem? Anyone got any ideas on how you solve that problem? What I've just described to you in that kitchen is what in computer science we call a race condition. We call that a race condition, okay? So 2 people accidentally salt the soup, okay? And you've got a nice safety mechanism there to avoid it, but the safety mechanism isn't quite right, okay? Well, you can just say only one person salts the soup, but that doesn't give you any parallelism, okay? It's more flexible if you've got more people who can do it, if you had a mechanism to allow that. You could assign everyone an individual task. Yep, that will solve the problem, but doing it that way reduces concurrency, reduces parallelism, so it can slow stuff down, okay? Maybe this is a little bit contrived. Maybe you want your kitchen... Maybe it's a bit ridiculous to have multiple people being able to salt the soup, but the point is that if more people are allowed to do it, then you have more possibility that things will happen the right way. So how can you do it if you have multiple people? Okay, If you only have one person salting the soup, again, that's very limiting. Okay, so I want to allow it that multiple people can do it, and just whoever's available does it first. Right. Someone said basically you've got to do the checkbox and the salting at the same time. That's what someone said, and that's exactly the answer. Okay, that's exactly the right answer. Okay, is it what? And that's the computer science answer. We make it atomic, so it is you don't salt the soup unless you check the box, and you don't check the box unless you salt the soup. They both must happen at exactly the same time somehow. Okay, how you actually implement that in the kitchen is another matter. But basically, you put in place a thing that says that the flag that says it's done is the same. Always happens at exactly the same time as when you actually do it. All right. And by the way, you guys should be familiar with this because there's another example. Well, maybe you're not because you're all too young. But back in the day, we used to get cash, like money in paper or plastic money, and we used to get out of machines, right? You go to a machine, right? You put your card into the machine, and cash comes out, right? You put your card in the machine, and cash comes out. Now, two things are going on there. One is cash is coming out, and you're going to get that, right? And the other thing that's going on is that money is taking out of your account. Actually, this happened to me not that long ago. I needed cash for something at short notice, and I just went to a machine, actually in Kingston, and it said, "Yep, we've taken the money out of your account. Your money's all there," and then the money didn't come out. Right? The money never came out. I'm like, well, that's bad. So I took a photograph and so forth. Anyway, they didn't actually take my money out, but I was worried that they had said we're taking your money out, but they didn't actually give me the cash. You want both those things to happen at the same time, okay? You don't want it to be the case that the person gets the money, but they forget to take it out of the bank. You don't want to be the case that it comes out of the bank and they don't get the money. We talk about that as atomic behavior. You want them both to happen or neither. Same with the salt. You either want to check that thing on the box saying the soup is salted and the salt actually went in, or, but you do not want one or the other. They both happen or neither happens. Okay. So you're doing one or the other, right? And so this is what we call atomicity. Now, one last slightly belabored example. If you've been to a large commercial kitchen, one of the things there is they've got lots of ovens in a big restaurant. You'll have actually quite a few ovens, right? Which is cool because it means you can prepare more meals at once, right? But if I said to you, hey, I want you to make this cake, and you said, sure, that'll take an hour and a half. And I said, don't worry, I've got 10 ovens, you can do it in 15 minutes. That wouldn't actually be helpful, right? Because having 10 ovens doesn't make the cake get baked 10 times faster, right? Everyone get that? So parallelism does not apply to every task. Some tasks can't be parallelized easily. If, on the other hand, someone said, I want you to make 50 cakes for this cake store, and you said, great, I've got 10 ovens, well, then maybe I can make the 50 cakes 10 times faster with the 10 ovens, maybe, right? But it will not solve the problem of cooking a single cake. The single cake is still going to take just as long as before. It's just if I'm doing 50, maybe I can do it 10 times faster if I've got 10 ovens. Okay? So hopefully you've got a bit of a sense there on some key concepts in concurrency and parallelism, and also this idea of atomicity, that we don't want to mark off the soup as being salted unless the soup actually got salted, and we don't want to salt the soup unless we mark it off. They both have to happen or neither. All right, and that's that concept of atomicity. Now, my keyboard, no, there we go. All right, so now back to the slides here. Concurrency, let's hear some definitions. Concurrency, multiple activities appear to occur simultaneously. So I'm not actually recording, well, I am recording, but actually here I've got two computers. I've got multiple computers here. But when I regularly give this in a lecture theatre, I'm recording on the same one that's running the PowerPoint's running on the same thing that's doing the recording. Now, one of the things that's interesting is, of course, the computers I have here have processors on them which allow multiple threads to run at once. I forget how many, but maybe 8 per computer. So that's 16, 8 threads here and 8 threads there. Okay, but it's not that long ago that a lot of them only had one. Okay, but nonetheless, they could still do, or at least appear to do, multiple things at once, and that's what we call multitasking. That's when we do one thing for a brief moment, then another thing for a brief moment, then we go back and do the other thing, and we keep doing this, and it has the appearance of doing two jobs at once. And one way to think about that is the 7-Eleven store where maybe the manager says, hey, tonight I want you to completely reorganize that entire shelf over there. And of course, you got to keep serving the customers. So you're doing two things at once, but you're only doing at any moment in time one or the other. You're either serving the customer or you're doing a bit more of that job of reorganizing the shelves. Okay, that's what we call time slicing, and that's what we call multitasking. Okay, so you're going to do shelf reorganization, but when the customer walks in the door, you go back to the checkout, serve them, and then you go back to organizing the shelves. All right, that's multitasking. And now a process is what we call distinct execution context, which shares nothing. Okay, so when on my computer I've got Eclipse or IntelliJ, I've also got PowerPoint, I've got OBS over here, I've got a Chrome browser, and I've got Zoom running here and so forth, and I've got Teams running there. All these things are happening at the same time, but they have nothing to do with each other. Okay, those applications, well, most of them don't, but don't have much to do with each other. They're separate processes. On the other hand, a thread is where you have multiple processes solving one problem. And I haven't updated the slide. It says Eclipse, which we used to use years ago. But in IntelliJ, you'll find that there are lots of threads which are all working together to make IntelliJ work. Now, you can actually do this on most computers. You can do something like this. Where is it? Here. Go to this. Now, that's tiny, but if you look closely there, you'll see, what does it say there? It says, oh, on this laptop, this is my little laptop. This is not my big work computer, which is over there. On this little laptop, we've got 1,347 threads running at once. Okay, that's a lot of threads. And if you look here, some of these things, what's this one here? 50. IntelliJ, if you look at IntelliJ here, it's got 50 threads running. 50 threads running. What's this one up here? Java, there. I've got no, Chrome. Chrome has got 28 threads running. There are 28 threads in my Chrome browser. And I think the only thing I've got up there is just the course web page. Let's have a look. Yeah, just got the course web page and it's already got 28 threads running. All right, so got a lot of activity here. Now, 1,300 threads, and I'm not using much, right? This is a reasonably good laptop. It's reasonably recent, but there's 8 processes, and somehow or other, those 1,000 things are all happening on just 8 real processes. Okay. So you can do this on your own computer and you'll get a sense of all the stuff that's going on, all the stuff that's happening at once, and these things are all doing different jobs. And the point here is simply that this is multitasking. PowerPoint is a separate process to Chrome, separate to Java, and separate to IntelliJ. And each one of those inside of them has got multiple threads running. All right. Now, let's go back to PowerPoint. All right, I think that's about it. So why do we use threads? Well, we use concurrency to separate. Oh, there's multiple reasons. Okay, why do we have threads inside of IntelliJ? It makes it helpful to separate concerns. So we've got a thread here which is doing a constant job of, for example, rendering the screen on IntelliJ. And another thing is going and compiling the code. You type some code, it's checking to see if it actually works, or putting a red squiggly line under it. That's a different thread. Okay, so this is good for different tasks that naturally occur. Like in the grocery store, you've got one thread doing the shelf stacking, and another thread doing mopping the floor, and another thread serving the customer. Okay? Parallelism is where we break things into pieces and exploit parallel hardware. That's where we've got 10 cash registers and 10 cashiers, right? And that's really good when you want to get a lot of stuff done at once. But it depends on problems that can be readily petitioned. And I gave you an example before of a ridiculous task that you can't readily petition, like cooking one cake. You can't petition that, so that's not one that lends itself to parallelism. But baking 50 cakes for a cake sale is something you can parallelize, right? And with that, we're done with the second from last module in the whole course. And I'll just put up the mini quiz here, publish the poll. Okay, and then we move on to the next section. Pretty much on time here. I'm going to push through and finish this section. I should finish it on time, but if I don't, I am going to go slightly over because this is the end of the whole course and we're just about there and we're just about on time. So if you have to stop at the hour sharp, then please just catch the video. So a thread is like a worker. So if someone asks, what is a thread? A thread, to go back to my analogy, the thread is the person. Okay, so at the grocery store, the 7-Eleven had one thread. One thread was doing all these different jobs. Okay, one thread is one worker. So we often use the word worker when we talk about threads. So a thread is one worker, in the grocery store there were maybe 20 workers in the big grocery store, and each of those you can think of them as being a thread. Okay, it's a concept of concurrency. process is a completely separate thing. So imagine if you go to somewhere, you've got a Coles and a Woolworths. One process is Coles, another one is Woolworths. They have threads inside of them, lots of workers, but they don't share anything. They've got nothing much to do with each other except they happen to be on the same real estate. Okay, they're quite separate stores. They're doing quite separate things. They have nothing to do with each other. Whereas in the in the Coles, within the Coles, all those workers there are like threads. They share everything. They share the same store. They have the same manager. They may even be able to do jobs for each other. So someone who's cleaning the floor can go and stock shelves and so forth, right? So they're sharing everything. Whereas the person stocking the shelf at Coles isn't going to be mopping the floor at Woolworths unless they've got two jobs, right? So that's the concept of a thread. The thread is the worker, and the process is a whole group of workers, which could just be one, right? So now let's get back to, oops, wrong one. Let's go back to where we were. Okay, Java threads. So that previous unit was all about the broad idea of threads. Now we're going to talk concretely about how Java does threads. Okay? So thread class is a class that is used to create threads and interact with them. Okay, so there's a class called thread. Now before we go any further, I just want to ask you a question. In all the stuff we've done in the course so far, notice this is right at the end and I'm finally introducing threads. That's because it's an important idea, but it's not a core idea for this course. We don't go and implement this in our assignment or anything like that. However, those of you who are sharp or have been thinking careful about this may have noticed that we've actually been doing threads under the hood somewhere here. Through the semester, the threads have been actually going on, but not explicitly. Does anyone know where that's been happening? We have been under the hood. There's threads been going on. Does anyone know where? The answer is in JavaFX. JavaFX has threads. Okay, so while one thing's drawing the picture, another thread is sitting there listening to events. Yeah, Jack says events. Yeah, exactly. So we've got in JavaFX, it's actually got a thread sitting there waiting for the key press or waiting for the mouse click. Okay, and that is in a separate thread. Okay, and so actually JavaFX uses threads, but it brushes over that detail, so you don't see it. If you study how to use JavaFX, it doesn't say anything about threads, but there are threads going on in there. Okay, now at this point in the course, we're actually going to look at threads quite explicitly. So Java has a class called thread, and you can use that to create a new thread. Okay, so there are two ways to do this. One way is to use subtyping, and the other way is to use an interface. Okay, and why would you? So there's two quite separate ways of doing it. Someone asked on Piazza, a good question, why do we use interfaces for the collection types in class? And someone gave a really good answer on Piazza just in the last 24 hours. A really good answer to that. And I also point out that the one of the reasons why for the collection types we use interfaces because that's how Java does it as well, which is not a strong reason, but that we are modeling what Java does, right? So why here in this case does it give you both choices? You could either use an interface by implementing the runnable interface, or you could use inheritance by inheriting from thread. Does anyone know why? Well, the answer's on the slide right in front of you. Okay, so the advantage of subclassing is that you get all threads methods automatically when you subtype, but the disadvantage is the class that did the extended thread can't extend anything else. So if you want to extend something else, then too bad. Okay, because Java has single inheritance. Okay, so we have both ways of doing it. If you can just subclass thread, you can say, your class extends thread. That's great, but the problem is that you can't extend anything else. You can only extend thread because Java only allows you to extend one thing. So you're done once you extend thread. On the other hand, if you did want something more flexible, you can implement the runnable interface and its run method. But that means you don't inherit the threads methods. You have to go and call them more explicitly. Okay? Do timelines run in separate thread? Yeah, I think so, Julian. I don't remember the insides of how JavaFX works, but they probably do. JavaFX extensively uses threads. What about both extending and implementing? Extending? Oh, I don't think you can do that. I'm not sure what would happen if you subclass thread and implemented runnable. That's a wild idea. You know what? You can try and do it while I'm talking and tell me what happens. It might just explode. I don't know. But no, normally you got you do one or the other. But it's a good question though. I just never really thought about it. I don't know what would happen if you tried to do both. It'd probably just tell you can't. I'm not sure. All right. Yeah, I'm just trying to think of a good answer to that. You'll probably find that you can't do it because there'll be things you can't extend, you can't implement. Anyway, give it a try and tell me what happens if you like. All right, so what do you get with a thread? You get a start, which starts that thread running. You get a join. Join is a really interesting idea. Join is the idea that says, I'm going to wait for that thread to finish doing what it's doing. Okay, so I'm going to sit here and wait until it's finished its job before I go on and do something else. Okay, because I don't want to start what I'm doing until that thing has finished its job. So join will cause me to wait until that thread has finished doing what it's doing. Very, very useful idea. The other thing you can do is you can sleep, which means I just want to stop for a bit, and that can be useful for a variety of reasons. Okay. Races. Okay, I gave the example about the salt, and I think everyone got the idea that what we really wanted was for the person doing the salting to simultaneously, or we'd say in computer science, atomically salt and check the box that says it's been salted, right? We don't want them to salt and not check the box. We don't want them to check the box and not salt. We want them to do both or neither, okay? And the synchronized keyword is a way we can have that effect in Java by making only one thread be allowed to do this thing. So if we can make a little method that says salt and check box, then if we use the synchronized keyword, we'd be guaranteed that only one worker would be able to do that method at a time. So if one of them's in the middle of doing it, no other worker will be able to run that method until the other worker is done. Okay. And so a race condition is a situation where one or more threads race to be the first to read or write a variable. This is where they're not controlled. The synchronized keyword allows us to control that. Okay, so you put that on a method, and it means that only one thread can execute that method at any moment in time. Okay, so it's something that only one thread can do at a time. All right, with that we can go on to the mini quiz, and then we can write some code. There it is. And let's write some code. So the very last bit of code for the semester. New package. J15. Already exists. What? J16. All right. Ah, the mini quiz is called J15. I've got myself out. Oh wow, I've got everything out of order here. That's the mini quiz for J15. All right. So anyway, I've given you the wrong mini quiz. Sorry about that, folks. Anyway, we're doing J16 here. I'm going to get rid of this. So wrong mini quiz up there. I've asked you the one about exceptions. I can fix that later. All right. So J16. We're going to create a class here. File new Java class. And what we're going to do is call it worker. And hopefully you can see the word worker is one we actually commonly use in computer science to describe these ideas. But also, hopefully you can see that the analogies, these metaphors I gave you about the grocery store and the kitchen and so forth, the concept of a worker, it connotes quite strongly to what I'm trying to explain. Okay, so what we're going to do here is we're going to implement runnable. Okay, so we're going to have a thread here, and then we're going to do it by implementing runnable. Now IntelliJ is saying, hey, you want to implement some stuff here? Implement the missing methods, and what we're missing is the run method. Okay, and that's the stuff that gets done when the thread starts to work. Okay, now what we're going to do is do something very simple. We're just going to have a pile of work, and we're going to eventually write a piece of code here that's going to get lots of workers to take bits of work off that pile of work. Okay, so try and think of a task that has a big pile of things that need to be done, and workers go and grab one, and the next worker grabs one, and so forth, and they grab the work. Okay, that's what we're trying to do here. Okay, and we're going to start off with just one thread, and then we'll add more threads to get this work done. Okay, so in work item, so work item equals 0. That's the work item we're up to. And then what we're going to do is we're going to have a fixed amount of work. There's no particular reason for this except that static final int work items equals 1,000. It could be any number. I just made that up. And then we'll say static final int workers equals 4. Again, that could be a different number. We're going to start off with 1 actually. We're just going to first of all have one worker, and then we'll introduce the multiple workers. And then what we're going to do is because our workers are actually incredibly lazy, they're not really going to do work. They're just going to pretend to do work. So we're just going to have this private void pretend to do work. Okay, so this is, you can just imagine they're actually doing something useful here, but we're not going to go and write code for that. So just imagine they're doing some actual meaningful task here, but for the moment they're not. All they're going to do is the following. They're going to say thread.sleep, and they're going to sleep for 1 millisecond. Okay, so instead of doing real work, they're just going to go to sleep for 1 millisecond. And then IntelliJ has said, hey, there's an issue here, and the issue is that the sleep can cause an interrupt, so we need to enclose with a try catch, which we'll just do there. Okay, so now we have our little piece of work that's going to get done, and we're going to do 1,000 of these. Okay, and 1,000 milliseconds, that's 1 second, right? So we've got 1 second's worth of work to do here, or 1 second's worth of sleeping to do, to be accurate. All right, now what we're going to do is in the run method, we've got to go, we've got to do this stuff here, and what we're going to do is we're going to say int. We're going to count how many tasks we do. So each, don't forget, this is an instance method here. These are instance methods, so each one is going to do this. We're going to say my tasks, so we can count up how much work we do for each thread. Each thread can count up how much they do. Yeah, there is actually a sleep method. It's quite useful for lots of stuff. So my tasks equals 0, like that. And then what I'm going to do is I'm going to get a work item. I'm going to get a work item number like I'm taking a ticket from the deli. So I'm going to say int my work item. Notice up here we've got work item, which is going to be shared by everyone. Okay, and down here I say int my work item, and then what I'm going to do is I'm going to grab a work item by incrementing this guy, and do stuff and keep going until the work items equals 1,000. Okay, so once we've done 1,000, then that's all. Okay, so we'll just say while my work item equals work item plus plus, that's up there, right? As long as that's less than the total number of work items, then we keep going. Right, I need parentheses here. All right, so let's just make sure everyone understands that. So this here is the shared work item that all our threads will share, okay? And I'm going to grab one, okay? And it's going to have a work number on it. It's like number 27. And I'm going to do that piece of work. And then once I'm done, I'm going to go back up here. And as long as there's still work items left to go, I'm going to keep going, okay? So I'll just keep going in this loop. And now when there's only one thread, this is completely obvious because I'm the only one who's updating this. And it's just going to go around here 1,000 times. And then each time I do this, I'll just pretend to do work. Okay? And then I'm going to add up how many tasks I did. Because the idea being that depending on how much this work takes, in principle at least, each thread could do a different amount of work, right? So at the end of all that, I'll say, I'll print out what happened. .out, .println, and I'll say, oh, I can say what thread number I am. Right, we can say thread, so I can actually find my own thread number. Each thread gets a number, right? So I can say thread. Well, better still, I can give each thread a name. When I create them, I can give them all a name, and so I can say, tell me my name. So I can say thread plus thread dot get current thread. That's me. Get current thread like that. Yep. Dot name. Get name, so that's the name of the current thread. And then I'll say that it did my tasks. Okay, so that way it'll say that this thread, whichever name we gave it, did this many tasks. Okay, so that's pretty simple, very simple piece of code here. All it's going to do, I'll just repeat, it's just going to go around this loop, incrementing the global thing here, this thing up here, which is going to be shared by everyone here. It's going to increment this and until we get to the total number of work items, which is set to 1,000. And each time we go around this loop, we do a bit of work, and then we go around the loop again, counting up how much we do, because each thread, everyone who implements this run method will have a different value for my tasks. Okay, so now what we need to do is to write our main method, psvm. Oops, nope, cancel. Now we need to write a main method, and we're going to create an instance of this class. James is jumping ahead of the game. So a question on the chat there. So good thinking, James. We're not going to use volatile in this class, but that is a good answer. You're on thinking along the right track. But I'll let everyone else just keep thinking and watching for a bit. So keep thinking, James. And also, we're not going to use volatile. So you think about what I said in the lecture about other ways to solve the problem that I think you've identified. Okay, so for those of you who didn't follow what I just said, then the code here is heading towards a bit of a problem, a bit of a disaster. We're going to have too much salt in the soup. Okay, and James on the chat has identified that, I think, and he's suggesting a solution for it. We're not going to go down his solution today in this class, but we're going to use a solution that I suggested in the lecture a short while ago. But you can think about that. Don't put it on the chat just yet. Just think about it, because I want everyone to see what goes wrong if things go wrong. Okay, so we're going to create ourselves a worker. And just, okay, like that. And so then we're going to create multiple threads. So thread equals new thread, like that. Thread. So I've created a thread. Okay, and then what I'm going to do, actually no, I'm going to create a thread called whatever, worker 1. Like it. Okay, so worker 1. That's what we're going to call it. And then I'm going to say I'm going to start my thread. Thread.start. Like this. Okay. And then what I'm going to do is print out all done. All right. So what should happen here? So Darren says he didn't know what James was talking about. You're not supposed to know, Darren. No one's supposed to know because I haven't taught this stuff yet. So don't feel bad, okay? James has got an inkling of something that I'm about to teach you in a minute. So don't feel bad about it. I'm going to explain it all in a moment. So just focus on what I'm talking about here, and it'll all be revealed. Okay, so what we've got here is we've got ourselves a worker. Oh, sorry. Yeah, here. I forgot to add worker here. Like that. So I'm creating a new thread using this worker instance here. And it's called worker 1. So that's our new thread. And I'm going to start that thread running. So it's going to go here and it's going to run this. It's going to go through this loop and then it's going to print out this. So now let's run this. Let's run this and see what happens. Okay. So I want everyone to think about what you expect to see happen here when I run this. Okay. We've got only one thread, so it should be really simple. Okay. Let's run it. See what happens. All right. Did anyone notice anything strange? Tell me in the chat if you saw anything strange there. What happened? What was strange there? Anyone see anything odd happen? No? Something odd did happen. What happened was it printed all done before. I'll run it again. It printed all done before the okay, so it was faster that time, but it printed all done before it did its work. Okay. So it printed all done, and then it said it did the task. So what's wrong? What's wrong? Anyone know what I'm missing here? There's something I just explained in the lecture a few moments ago. What's missing is I need to do this, thread.join. Okay, like that. Thread.join. And a join can also throw an exception, so we need to enclose that. Okay. All right, so we've got a thread.join. Video on YouTube froze. Oh, wow. That is weird. Okay. Alright folks, sorry about that. Another piece of hardware failed. It's just getting better and better. My video hardware just decided to, it was the end of semester, so it would just not work. Can't believe my luck here. Alright, so here we go. It should be on there. Okay, well, should be back. Apologies for that. All right. And back on Zoom as well. Hang on, lost it on Zoom. There, you should see it now on Zoom too. No, still not there. Blank screen on Zoom. Why is it doing that? Come on. There we go. All right. All right. So hopefully you've got a picture there on Zoom. Oh, it's done it again. Holy cow. All right. I'm going to, what am I going to do here? Man, this is so bad. Okay. Folks, hopefully you can now see that the chroma keys just decided to give up the ghost. I have no idea why. Nice expensive piece of hardware just failed on me. All right, you can see my mouse there. And all I can imagine, so hopefully you can all hear me and you can see the mouse move. All I can imagine here is that it's temperature related because today's actually a lot warmer and my office is actually hot. So something just gave up the ghost. I don't know why. All right. Let's see if I can continue here. Yep. All right. So things are working. You can't see my face. Sorry about that. Let's just keep going. Let's plow ahead. What I've done here is I've added in join. All right, so what happened was, this is so frustrating. Let's just do this again, folks. I didn't have this join here. Let's just get rid of all this code. And we'll run this. Okay. All right, so what you may not have seen there is that when this ran, it ran okay, but it printed all done before it actually finished doing the work. And so what I did then in response to that was to add this in, like that. We run this. Okay, and now we've got them in the correct order. Okay, so what I did was add in a join. Okay, so I added in a thread join there, and that way we got we started our thread and then we joined. All right, and what we're going to do next is actually I'll add multiple threads, which is the whole point of this exercise. Now we're running out of time because of the annoying technical problems. So what we're going to do now is make multiple threads instead of just one. Okay, so first of all we're going to say we're going to have an array of threads. Threads equals new or workers. Is that called workers? Didn't know. Workers. There we go. Workers like that. We're going to, so what's happened here? Oh yeah, thread. This, so I need to declare an array. It's an array type like that. And so now we've got an array of threads, not just one. Now we're going to write a for loop for int I equals 0, I is less than workers, I plus plus, and then we will assign each element of the array threads I equals new thread, just like this here. Cut that out from there and put it up here, and this will be worker I instead. So we've created a whole bunch of threads, not just one, and then we're going to start each one off. Okay, so like this, threads I dot start. Right, we can do that in a separate loop just for clarity. Let's do that. This. So I've created an array of workers. Now we're going to start them all off. Threads I dot start. And then what we're going to do at the end is we're going to go through all the threads and join them all. Okay, so we're going to say for int I equals 0, I is less than workers, I plus plus, this, and we're going to join all of them one after the other. In fact, I could just put this here. Let's just do that. There we are. Okay, so let me just get the indentation right. Okay, so what I've done there is change our code. So now instead of having just one thread, we have 4 threads, and this all should work. All right. Hopefully you all are still with me here online. I haven't seen anything for a bit, but hopefully you can see that, and you can tell me what's going to happen next. When I run this, what's going to happen? Okay, they're going to run. Let's see what happens when they run. Okay. Can anyone see an issue here? Can anyone see an issue here? James, this is your cue. Anything? Can anyone see what's going on here? Look over here, folks. First of all, you got 4 threads, not just one. That's good, okay? And look, all 4 threads finished, okay? That's good too. Right, as Paul says, you add all these up, they don't total to 1,000. Okay, we did more than 1,000 tasks. How can that be? Right? Why would it be more than 1,000 tasks? And I think James knows the answer because he made a hint about it. The problem is that they're all snatching at these numbers and they're racing. There's actually a race to get the number. So they're all racing to get this work item here, which is basically what James was hinting at earlier on in the class, okay? So the fact that the zero is not the first thread to finish doesn't really matter. They could finish in any order. So the fact that 0 is not first is not a problem. The problem is that they're snatching at this thing here and they're actually racing each other. How could that be? This looks like it's a single thing. I talked about atomicity, about the person checking off the soup was done and putting the salt in. You need to put them both together, right? Now you think here, he's just incrementing something. That's just like checking it off, right? It's not 2 things, it's just incrementing. That's the mistake. It's actually multiple things happening here. If I want to increment, what's actually going on in the computer is, in fact, this is read work items, increment work items, store work items. There's 3 activities. Now, if multiple threads try and do it at the same time, they can interleave. And so this one reads 100, then it goes and increments it, so it's 101, and then it goes and stores 101, right? All good, right? But at the same time, another thread comes in and it just reads it right after the other one, before this other stuff happens. So it also reads 100, okay? And it also adds 1, gets 101, and it also stores 101. Then another thread jumps in and does the same thing. You can see here, they're all racing and they're actually doing 3 things without being synchronized. Then you can get this behavior. So let's try and fix this. The way we can fix this is by doing what? We can use the synchronize keyword by making that stuff be one atomic thing. So what we can do here is we can say private int inc work item, right? And then we can say return work item plus plus, right? And then here we just say inc work item, okay? Inc work item. There we go. So we do this. That won't fix our problem, but I just want to show you that this is the same. All right, got the same problem, right? The numbers are slightly lower, probably because the program is now slightly slower, but you got the same problem. Okay, keep doing this, same problem. Okay, but what we can do here is say synchronized, right? Put synchronized there. Now when we run it, what do we get? 250. They don't all do exactly 250 because someone might start sooner than the other, but what you see here is that the total is 250. These 2 did 250, that did 1 less, and that one did 1 more. We did exactly 1,000 tasks, okay? And how do we do that? We did it by making the work item synchronized, by ensuring that the 3 actions that are actually happening inside of here, read work item, add 1 to work item, store work item, they're all happening. Only one thing can do it at once. So we can't have multiple threads coming in. While this one does the reads 100, say it's 200. This one reads 200, it adds 1 to it, 201, and then stores 201 to memory. Okay, and this one here comes in and it reads 200, adds 1, and so we didn't update it correctly. But when this is synchronized, this one can't come into that method until the other one's completely finished all those activities. So that way they're separated. Okay, so just putting that synchronized there solved the problem. And with that, we have finished the class. So sorry that we finished on a technological downer with the sucky video thing killing out on me. Yeah, only one thread can access the task. That's the way we solved the problem. We solved the problem by saying only one thread can access that variable at any moment in time. And that's ultimately what you need to do here. You need to make sure that only one thread can access the variable at a time. With that, let's move on to our final bio. So our final bio is Anita Borg, very influential person. She died relatively young of, I think, breast cancer. But she was a very influential computer scientist who really pioneered women in computer science. And there's a whole network that sprung up around her. She was a very influential person with a PhD from New York, NYU, that's the New York University. And she worked in an area that's not too far away from me. But she has an enormous legacy. And in fact, only a few weeks ago, I gave a talk at the Grace Hopper Symposium, Grace Hopper Celebration of Women in Computing. I gave a talk there just a few weeks ago, and that is a legacy of hers. And it's an absolutely enormous conference with like 10 or 20,000 people attended each year. It was done virtually this year, of course, but that's what part of Anita Borg's legacy. So a very important, influential computer science who really paved the way for a lot of women in computer science. So with that, I will finish up and we're done for all of the teaching in this class. Monday, we're going to do exam revision and hopefully my technology will hold out for the final lecture of the course. So Monday is our last lecture for the course, and in that one we're doing exam revision. And please think about what you want to ask me, and the best thing to do is to put it on Piazza well ahead of the lecture so I can see what you want to ask. Obviously I can just do it on the fly through the chat, but if you've told me in advance, your question will be higher up on the priority list. Okay, with that, have a good day, and hopefully you'll have a good weekend. You've earned it with your assignment being due. So see you later.